Okay, here are some solutions to our practice test. I have inserted a little picture of the periodic table because we're going to use that for this. So, it goes like this. For our first question, we're using the periodic table and we're figuring out the number of valence electrons, protons, neutrons, and electrons for these different atoms, elements. So first, let's take a look at carbon on the periodic table, and if we, oh good, we can zoom in. So if we look at carbon, this is a picture of the textbook. We can ignore this writing here. So carbon, right here. First of all, this is row 1, okay, or energy level 1, and this is energy level 2, or row 2. And as we sort of go across, it indicates the number of electrons that the element will have. So hydrogen has 1, helium has 2, and those are both in the inner shell. And then in the second shell, or energy level, lithium has 3, beryllium 4, boron 5, and carbon 6. So it'll have a total of 6 electrons, but it has 2 in the inner shell, and then 1, 2, 3, 4 in its outer shell. So those will be its valence electrons. In addition, look, we have a blown up version here. So 6, this is the atomic number. That's the number of protons, its symbol, and then down here its average atomic mass, which rounds to 12. So most of the atoms will have an atomic mass of 12, meaning 6 protons and 6 neutrons. So, number of valence electrons carbon has, that was 4. Again, 1, 2, 3, 4. The number of protons, it has 6. That is its atomic number. That will never change. And the number of neutrons that most carbon atoms have is 6, because 6 plus 6 gives us 12, which is, if you look closely, the average atomic mass. And then the number of electrons should be equal to the number of protons, unless it is an ion, meaning it has gained or lost an electron. Next up is carbon 14. So we have, this is like a isotope notation, where we have the symbol for the element, and then this is its atomic mass. So if the atomic mass is 14, and so this is atomic mass, and the number of protons is 6, we know that 14 is, that's an equal sign, 6 plus the number of neutrons, and solving that would give 8. So everything else stays the same. This is an isotope, meaning the number of neutrons will be different from normal, but everything else stays the same. So it has 4 valence electrons, has 6 protons, 8 neutrons, and number of electrons and protons is the same. If we look at hydrogen way up here, little hydrogen just has 1 electron, 1 proton, no neutrons, and 1 electron. Simple little atom. Calcium, on the other hand, is farther down. Whoa, that's cool. And so calcium is right here. And so we have 1, 2, 3, it's in the 4th energy level. And when we count inward, we have 1 and then 2. So it's in its outer shell, it's going to have 2 valence electrons. So let me see if I can show you what that would look like. I wonder, oh yeah, good, this is totally going to work. So let's try this. We would have its nucleus, and then 2 in here, and 8, and 8 in its third energy level, and then in its fourth energy level, it would have 1, 2 electrons. So these are all filled up, and I'm not going to draw them all in. We'd have 8 here, 2 in the inner, and then 8 here. But 2 valence electrons in its outer shell for calcium. So we have 2 valence electrons. And then for the number of protons, we really need to get in here and look. So what does it say? So it looks like a 20 right here. And then this, I know this is pretty hard to read, but you could be looking at your periodic table. I think that says 40.078, meaning it rounds to 40. So we have, and this makes sense, 20 protons and then an atomic mass of 40, meaning it would also have 20 neutrons. And again, the protons and neutrons will be the same for light elements, but once we get down here and they're heavy, the number of neutrons ends up being more than the number of protons. So for calcium we had 20 and 20, and then again electrons and protons should be the same, unless it is an ion. And lastly for uranium, and look at this, this is U-235, so that's the isotope that is commonly used in nuclear bombs and nuclear reactors. Down here, let's see if I can read uranium, and it looks like the atomic number is 92. 92, so let's put that number in before we forget it. The number of protons is 92. And valence electrons, let's see. We went, so the lanthanides and actinides kind of sit right in here. So we would go 1, 2, 3, and then 4, 5, 6. That's a little confusing. And I wouldn't actually ask you this particular thing on the test, but it's here, so I'm going to answer it. Just because going in here and then transitioning to the get it? Transition metals, ha ha ha. And then transitioning to these little rows, that would be a little weird. But protons, neutrons, and electrons for U-235 definitely. So protons, 92 protons, and then neutrons, if we know that the atomic mass is 235 and it has 92 protons, we would subtract to find neutrons. 235 minus 92. Love the math. And what do we get? Looks like a 143. Does that work out? Da-da-da and da-da-da and da-da-da. Alright, yeah, good. So 143 neutrons, and then the electrons would be same as the protons. So notice, please, how the number of neutrons is much greater than the number of protons, and that happens with the heavy elements, especially the radioactive ones. Okay, moving on. 2, an isotope of oxygen has 2 extra neutrons. How would we write the symbol for this isotope, and how many neutrons would it have? So we're looking at oxygen. Oxygen is atomic number 8 and atomic mass 16. So normally oxygen has 6 neutrons and 6 protons. But this is saying that it has an extra 2 neutrons, meaning it would have 8, giving it an atomic... Wait, I am wrong. I need to zoom in here. Aha! Okay, nice work, Tourville. Oxygen is 8 and 16. Okay, so 8 protons and 8 neutrons. I was thinking of carbon. So let's just erase that whole thing. Oh, look at these numbers got caught onto that. Oh, great. So what am I doing? I'm doing this. Forget I said that. So oxygen normally has 8 protons and 8 neutrons, but it has an extra 2 of those, giving us a total of 18 as far as its atomic mass. And so we would write it in isotope notation O, 18, like that. Its symbol, and then its atomic mass. Question 3. A sodium atom has lost an electron and is now an ion. How many electrons does it have? What is the charge of the atom? So let's again, oh dear, let's take a look at our periodic table. And maybe I can do it without moving it around. No. So sodium, it looks like 11 and 22. So let's put this back in place. Ooh, this is going to get tricky. So a sodium atom has lost, what was that? 11 and 22. Alright, so normally it has 11 electrons and 11 protons. If it's lost an electron, it has become an ion, so instead of 11, it would now have 10 electrons. And what charge would it have? So the charge would be +1. Remember, electrons are negatively charged, so if you lose one, you're losing the negative charge, becoming positively charged. Alright, list 2 elements from each of these groups. So the halogens are here. So we could say fluorine and chlorine. If I were just listing the symbols, I might do this. For the alkali metals, those are, yeah, sorry, this is getting a little messy here with the weird writing sticking to different places. Alkali metals, alkaline earth metals. We're going to be asked about transition metals, and then the noble gases as well. So alkali metals, we could list lithium and sodium. Lithium, sodium. Noble gases are way off to the right. How about neon and argon? Transition metals are all these in the middle. So copper, copper and zinc. Okay, those are things that you sort of experience on a day-to-day basis, like in coins or whatever. So Cu, Zn. And then the alkaline earth metals would be here. Magnesium, calcium. Magnesium, calcium. You might even find those things in Gatorade. Okay. Almost done here with page 1. How many energy levels would a calcium atom have for its electrons? So I think we talked about that right here. Let's just triple check by moving this periodic table around. Messing up everything. Yeah, that was the calcium atom. And so this calcium, we had the inner, and then 2, 3, and 4. 4 energy levels or shells. Okay, so we're going to stop here and then do a separate video for the second page, because this is getting totally messy. Oh dear. Okay, here's part 2 of our practice tests and solutions. Question 6 says, if an atom has extra neutrons, it can be radioactive, meaning it can lose those neutrons in radioactive decay, releasing energy. The half-life of radioactive carbon-14 is 5,730 years. How long would it take for 75% of a carbon-14 sample to decay, meaning there is now 25% left? So it would start with 100%, like this. And after half decayed, it would then have 50%. And once half of that decayed, it would then have 25%. So this means one half-life has passed and another half-life has passed. So that is 5,730 years plus another 5,730 years. 5,730 times 2 will give you, let's see, 11,460 years. I'm going to check that on the calculator here. 5,730 times 2 is 11,460 years. Okay. Question 7. The half-life of caffeine in your body is 6 hours, so this is similar to the homework question we had. If you assume you drink 100 milligrams of caffeine at Starbucks, please complete the table calculating how much caffeine would be left in your body after a certain amount of time. So, you have a cup of coffee, let's say there's 100 milligrams of caffeine in it. 6 hours later, half of that will have decayed, or your body will have basically broken down those molecules and got rid of them. So half of 100 is 50, so you would now have 50 milligrams left, because 100 minus 50 is 50. Okay, so this is the amount that disappears, this is the amount that's left. So this is how much you have left. After another 6 hours, half of this will disappear, so 25 disappears, leaving you with 25 milligrams left over. And then this is not another 6 hours, this is 6 hours and then another 6 hours. So half will disappear, and then another half will disappear. So the in-between value, half of 25, is 12.5. Okay, so at 18 hours you would have this much, and then once half of that disappears, you will have 6.25 milligrams. 12.5 divided by 2 is 6.25 milligrams. Okay, let's see. 8. List one reason supporting the statement, it was a good idea for the U.S. to drop nuclear bombs on Hiroshima and Nagasaki in World War II. So we went through those guided notes, and I think the strongest reason we came up with was that it ended the war early. So you could say something like, ended war early, and this was the war with Japan. The war with Germany was already over. It also almost definitely saved the lives of U.S. soldiers. So American or U.S. lives. And then the next question, list one reason supporting the statement it was a bad idea for the U.S. to drop nuclear bombs on Hiroshima and Nagasaki in World War II. So while it did save the lives of U.S. soldiers, meaning they weren't over in Japan fighting for another year, it killed hundreds of thousands of innocent civilians. Killed, and I think it was about 200,000, so let's just put that. 200,000 innocent civilians. Meaning women, children, non-soldier type people. 10 lists three sources of renewable energy. So we have solar, we have wind, we have geothermal, hydroelectric, and because many of us have wood-burning stoves in our houses, we could say wood, because trees do grow back. 11 lists 3 sources of non-renewable energy. So these can be fossil fuels, like coal, oil, so gas, and then also we're going to say plutonium, uranium, because those are used in nuclear reactors, which generate something like 15% of the United States electricity. 12. Please study your 47 vocabulary flashcards. You have several matching and true-false questions directly from the definitions on your cards, so you have them. We had lots of time in class to put them together. Please do study those. And thanks. Please study, study, study. The test is going to be really similar to this. So if you go through this and you've got this far in watching these video lessons, that's probably a really good sign. And you should do very well on this test, and it'll be good for your grade.